Hi everyone, my name is Ja. I'm presenting our work on individualized prediction of task contrast from resting state functional connectivity. I will present a novel surface-based neural network that vastly improves over existing baselines. We also derive a reconstructive-contrastive loss that trains the model to generate highly individualized brain images. There are two main paradigms of fMRI. One is resting state fMRI, which captures the time series of spontaneous brain activity while subjects are at rest during the scan. The other paradigm is task-evoked fMRI, in which brain activities are measured while subjects perform specific cognitive tasks. In this paradigm, what researchers most interested in is often the contrast of tasks. For example, how are the subject's brain activated differently while listening to a math question as compared to listening to a story? So, one question that has been asked is, can we use resting state fMRI to predict task contrast? The answer is yes. For instance, previous work by Tavor and Cole have demonstrated that such prediction is possible with well-crafted linear models. In this work, we show that we can achieve even better individualized prediction with neural network. Here's the overview of our approach. We proposed BrainSurfCNN, a meshed Bayes convolutional neural network architecture that operates on the cortical surface. We also propose a reconstructive-contrastive loss that both minimize the same subject's predictive error and maximizing the across subjects difference. Input to BrainSurfCNN is a functional connectome derived from the resting state fMRI time series of the subject. Let's say we pick a particular region of interest, or RRI, from the brain and compute the mean time series over all the vertices in the RRI. We can then pick a vertex time series and compute its Pearson's correlation with the RRI average time series. This gives a functional connectivity measure between the vertex and the RRI. Repeating the computation for the entire cortex, and we get the whole cortex functional connectivity with a given RRI. And if we repeat the procedure for all the RRIs in the brain, we get the functional connectome. Now we can see that the functional connectome is analogous to a multi-channel image. The cortex is equivalent to the grid of pixels, and each RRI corresponds to an image channel. In our experiments, we used 50 RRIs, and each brain image is represented by a standard FSLR mesh with 32,000 vertices on each hemisphere. The FSLR mesh of each hemisphere is derived from an icosahedral sphere. The two spheres are symmetric, and we can concatenate them along the channel dimension. For example, with input connectomes derived from 50 RRIs, the concatenated input is a spherical mesh with 100 channels. The model's output is a subject's task contrast. Each task contrast is also represented by a 32K FSLR mesh. We predict all the task contrasts simultaneously as a multi-channel brain image, with each channel corresponds to one task per hemisphere. BrainSurfCNN has the architecture of the U-net, commonly used for segmentation. It has one downward branch that doubles the number of channels at each level, and the resolution decreases from 32,000 to 10,000 and 2,000 vertices. The upward branch has the inverse structure to recover the original resolution. There are also the seed connections from the downward to the upward branch that improves the predictive quality. To train the model, we proposed a new reconstructive-contrastive loss. The composite loss has two components. The reconstructive component of the loss is the usual error between the prediction and the true task contrasts. The contrastive component is the average difference between a subject's prediction and the task contrast of all the other subjects in the same batch. In our experiments, we chose L2 as a measure of error. Finally, we combine the two components using two margins. Alpha is the same subject margin, and beta is the across subject margin. Intuitively, what this loss does is to enforce the same subject error to be within the margin alpha, while encouraging the average across subject difference to be large, controlled by beta. We use data from the Human Connectome project in our experiments. Each subject has 4 runs of resting state fMRI. Each run is 15 minutes long with 1200 time points. We split each run into 2 samples, each with 600 contiguous time points, resulting in 8 functional connectomes per subject. Generating more samples per subject is a data augmentation strategy, and also as an ensemble learning strategy, we average the 8 outputs to get the final prediction for the subject. There are 47 task contrasts available per subject, 23 of which we found to be reliably predictable and used for evaluation. We use the 50-component ICA from HCP to derive the functional connectomes. There are 900 plus subjects for training and validation, and 39 test subjects for evaluation. The 39 test subjects also have retest data, which are data collected with the same procedures on a different day. We compare the proposed BrainSurfCNN with 3 baselines. First is the linear regression model proposed by Tavor and colleagues. As a lower bound, we use the group average task contrast. This lower bound is dependent on the degrees of inter-subject variability within each task, which will be high for tasks with low inter-subject variability and low for tasks with high variability. As the upper bound on performance, we use the retest task fMRI scans. The retest scans were also used to quantify the reliability of the contrast maps. This box plot shows the Pearson's correlation between the model's predictions and the true task contrast across all test subjects and the 23 reliably predictable tasks. The higher the correlation, the better. The linear regression baseline is in yellow, BrainSurfCNN is in orange, retest is in green, and the group average baseline is in blue. As we can see, the orange bars of the BrainSurfCNN is better than the baselines across all tasks. Here is the contrast map of 2 back-working memory tasks for 1 sample test subject. The reddish areas indicate the activated regions, and the blue areas are the deactivated regions of the brain. The next row shows the task contrast measure on the same subject in the retest section. We can see that the task contrast of the subject across the 2 sections are very similar. The number below the brain is the Pearson's correlation coefficient between the true test contrast and the retest contrast. Next, we have the 3 predicted maps from the BrainSurfCNN, linear regression and the group average contrast. Prediction from the BrainSurfCNN is the closest to the ground truth in terms of Pearson's correlation. Visually, we can also observe BrainSurfCNN prediction captures features that are missed in the baselines. For example, zooming into the circled area of the prefrontal cortex, there are activated brain regions in the true contrast map. And these activated areas are also correctly predicted by the BrainSurfCNN model, but are missed in the linear regression baseline. We also quantify the model performance in terms of subject identifiability accuracy. This accuracy measure indicates if the prediction of a subject is closest to the given subject task contrast than all the other test subjects. In this measure, BrainSurfCNN is better than the linear baseline for all tasks. This suggests that the training of the proposed model with reconstructive-contrastive loss can produce highly subject-specific prediction of task contrast. In conclusion, we proposed BrainSurfCNN, a surface-based CNN for predicting task contrast from functional connectomes. By training with reconstructive-contrastive loss, the model can achieve both predictive accuracy and subject identifiability. The model's code is available online. Thank you for your time.